When nickel chloride is added to water, it dissolves readily. Because more nickel chloride could be dissolved in this solution, the solution is called unsaturated. When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
So two terms we're going to use to describe what happens when compounds dissolve in water are saturated and unsaturated. And to figure out when something is saturated or unsaturated, we need to know about the solubility. So what we're talking about here is when you have a compound that dissolves in water, how much of the solute can dissolve in water, all right? And the solubility is literally some kind of maximum amount that can be dissolved in that amount of solvent at that given temperature. We'll see later that it's temperature dependent. So as an example, if you take the green nickel 2 chloride and you dissolve it in water and you stir it up, all the solid goes away. That's considered an unsaturated solution because you could probably put more nickel 2 chloride in there, stir it up, have it dissolve, go away. All right. So an unsaturated solution just means you can add more solute to the solvent that you have and it'll keep dissolving. And there's a temperature dependence too, but that's not as important. So unsaturated means there's more room for solute to dissolve in the amount of solvent that's present in your solution. Now, there comes a point though where you can't add any more solute, and that's when you have a saturated solution. So you can think about all of the solvents as having a capacity for dissolving solute. And once that capacity is exceeded, like it was there in the yellow solid in the upper right-hand corner, then you have a saturated solution. So in a saturated solution, you will see the solid. You can stir and stir and stir, and it won't dissolve back into the solution. It stays as a solid. And all compounds have a saturation point. This will be something we'll talk about more in Chem 223, how to predict when you get to the saturation point. But it's just something to consider. But if you see a solid, then that means that your solution is saturated. So insoluble compounds have a pretty low saturation point because it's easy to see the solids and stuff that form. You can't dissolve and make them go away. We'll come back to this in a later lecture.
When supersaturated sodium acetate is poured onto a few grains of solid sodium acetate, the amount of sodium acetate dissolved in excess of the saturation point precipitates, forming a solid. Some of the liquid solution, which is now simply saturated, becomes trapped within the solid.
There is also what's called a supersaturated solution. And this is kind of a specialized application, but it can be useful when you're trying to crystallize compounds that you make out of solution. But anyway, in a supersaturated solution, these are always unstable. And usually what happens is they'll heat up a solution to a warmer temperature. And the amount of solute that dissolves depends on not only the amount of solvent, but it does depend on the temperature. And generally, at warmer temperatures, you can dissolve more solute at a warmer temperature than you can at room temperature. So if you have one of these supersaturated solutions, usually the solvent has been heated up. You can add a lot of solute, and then if you cool it down and you disturb it, like if you have a little seed crystal to get it started, then all of a sudden you start making solid like crazy, and you can make some kind of cool geometric structures. Anyway, this is kind of a specialized application of solutions. But if you hear about supersaturated solutions, they are a little unstable. You can't just carry them around and stuff like that and expect them to do it. And once you disturb them, they will start saturating out right away. And sometimes the results are quite impressive, as you can see from that wild kind of structure there. Now, we've talked mostly so far about solutes and solvents where the solute was a solid, but you can also have gases dissolved in liquids too. That's not a problem. And generally speaking, gases are usually more soluble in liquids at lower temperatures. As you get to higher temperatures, then the gases have extra energy and they're able to essentially break away from the liquid. That's what I think about. So a lot of times, if it's a hot day, you want to open up a carbonated drink, a Coke product or beer. Beer if you're 21 and over, 19 in Canada. But I know that joke gets kind of old after a while. But anyway, carbonated drinks are usually more bubbly if they're in the refrigerator, all right? Because colder temperatures, the gases dissolve better. And as you start warming it up, then the carbon dioxide comes out, that fizziness happens, and it usually makes the drink more attractive to people. Not always, but most of the time. So Henry's law is actually a mathematical relationship that talks about how soluble a gas is. And solubility, which gets the symbol capital S with a little g, is the solubility of the gas. And it depends upon a Henry's law constant. And these are things you either determine or you can look up in a book, something like that. And it does depend on the partial pressure of the gas over the liquid. And the more partial pressure you have, the more soluble the gas is in the liquid. On the other hand, if you don't have a lot of the gas above the liquid, then the gas is not very soluble. Henry's law is used a lot by the soft drink industry to kind of make the best combination of carbonation with their drink possible.
When a can of soft drink is opened, a whooshing sound is heard, and the solution begins to release bubbles. The escaping gas is carbon dioxide. Henry's law explains why the gas leaves the liquid only after the can is opened.
So when you pop the top of a soft drink or some kind of beverage like that, you hear that hissing sound and stuff, and you pour it, and inevitably what happens with me is the liquid goes over the container side of the glass. But anyway, that's just me being clumsy. But anyway, the idea is that if the external pressure drops, then the solubility goes down. So on the right-hand side, look at those two pictures right there. Let's look first at the bottom one. That represents a high pressure, like they're pushing down on it. And you can see that there's lots and lots and lots of little purple gas molecules dissolved in the liquid. There's some above the liquid totally, but there's a lot of them beneath it. Well, in the upper example, we haven't totally popped the top, but we have lowered the pressure. And you can see how there are fewer of the purple gas molecules in the liquid. Most of the purple gas molecules are over the liquid. So as the pressure goes down, the gas isn't as soluble. You don't have as many gas molecules in the liquid, which is kind of interesting. There's an example of a Henry's law constant for oxygen, 1.66 times 10 to the minus 6 molar per millimeter of mercury. Millimeter of mercury is what the pressure of the gas is usually measured in. Remember, a millimeter of mercury and a torr are the same thing, and 760 millimeters of mercury equals an atmosphere. And the big M, the molarity then, is the solubility of the gas in the solution, which is kind of cool. So here's a kind of question you might see. It says, after a can of Diet Coke is removed from the refrigerator, opened and left to stand a while, which of the following best describes the changes that cause the soda to go flat? And going flat, again, just means that it doesn't have any more carbon dioxide in it, basically. But anyway, here's the different possibilities. It says lowering the carbon dioxide pressure over the solution and raising the temperature is what happens to make the flatness appear. You could also say lowering the CO2 pressure over the solution would be a possibility. Lowering the temperature would be one answer. And you can increase the salt content. Well, first of all, on D, we're not adding any salt, so that doesn't make any sense whatsoever. However, if you think about it, if you open the can, you're lowering the CO2 pressure over the solution, and that's going to make the CO2 rush out. In this example, you're also allowing the Diet Coke to stand at room temperature for a while, and that's going to raise the temperature. And both of those things will definitely affect how much CO2 is present. So if you raise the temperature and open the can, it's going to go flat a lot faster. If you open the can at a lower temperature, it wouldn't go flat quite as quickly. You can kind of see how this works. And people that work in the soft drink industry often have to think about these kind of considerations when making their soft drinks. Gases in liquids become less soluble generally as temperature goes up. All right. And again, you can think about gases as having more energy, so they escape, et cetera, et cetera. However, generally, solids and liquids become more soluble generally as the temperature increases. So in that graph right there, you can see that almost all of those compounds, sodium nitrate in the upper left, calcium chloride underneath it, lead 2 nitrate, et cetera, almost all of them are going up as the temperature, the x-axis, increases. However, that's not all the time the case. So down there in the lower right-hand corner is this weird cerium sulfate compound. That's an example of a compound that becomes less soluble as temperature goes up. And we'll talk about this more in Chem 223, why that kind of thing is possible. However, in general, ionic compounds become more soluble in water as the temperature goes up. Liquids in liquids can be infinitely soluble if they have similar intermolecular forces. So, for example, water in ethanol, water in acetone, all these kind of similar things, if they're liquids, they should be able to dissolve almost forever. They're considered to be miscible. Miscible is a term that means that they get along really, really well. They're usually for liquids. And if they're similar intermolecular forces, they should just dissolve as long as you can. So there's lots of examples of this. If your car has a radiator, it probably has some kind of antifreeze in it, and that antifreeze is essentially a hydrogen bonded containing species that dissolves well in water. You can pump that up as long as you want, no problem. They're very miscible. Immiscible solutions usually are liquids with different intermolecular forces. So again, that oil in water example we mentioned earlier, oil is basically induced dipole. Water is hydrogen bonded. Those two forces don't get along. So in that glass container right there, the top layer is some type of oil. The bottom layer there is like water. It's clear. And they don't get along very well because they have different intermolecular forces, which is kind of cool. So miscible just means liquids dissolve really well in each other, and you can basically add them, and you'll never have any problems. On the other hand, immiscible means they don't have similar forces, and they generally don't dissolve very well.